So here I would like to show you the same things actually, but using the Navier Stokes equation. So we will see the fully developed flow between parallel plates using Navier Stokes equation. The flow field between parallel plates will be derived here using the continuity and Navier Stokes equation. Reference is made to above mentioned figure where y is the coordinate normal to the plate and x is the flow direction, same as s direction. So the idea is simple. Once we try to develop the equation from the Navier Stokes equation. So I just list down all the assumption here. So first, because it is fully developed, so the derivative of du dx and dv dx is equal to 0. So and then because it is a steady flow, so the du dt and dv dt are 0. So I think we discussed about the simplification of Navier Stokes equation previously. So and then we have the gravity. So the gravity, you know that in this situation, so the gravity is pulling vertical like this, but in this direction, so we need to calculate the gravity in terms of the component of the velocity, because will give us okay the component of this one, because we have another component of this one, perpendicular of this one. Okay. So and then if we calculate the gravity, so we will find that the gravity is actually the x direction is g sine theta and the y direction is negative g cos theta. So because we are using Cartesian coordinate, so the continuity equation is remain the same like this. So we have du dx plus dv dy is equal to 0. So in this situation, we only think about a two-dimensional plane. So and then again, if we substitute according to the simplification that we have, so we get the du dx is equal to 0, and the continuity equation will reduce into dv dy is equal to 0. So and then the v is constant. So and then again we could determine that actually the velocity v is 0. So means that this is just to prove that the velocity on u component on the u component is occur in this situation, in the real situation. Okay, so this is the Navier Stokes equation in the y direction. So here we take, because we have a situation like this, so we assume this is y and this is x. Okay, so because v is 0 everywhere, there is no acceleration in the fluid in the y direction, so the component of the Navier Stokes equation reduced to dp dy is equal to negative rho g cos theta. So integrating over y, one has p equal negative y rho g cos theta plus p pressure at y equal to 0. So where the p at y equal to 0 is the pressure distribution along the lower wall, the equation shows that the pressure decreased with elevation in the duct as expected. In fact, y cos theta is equal to z, so this equation can be written as the equation of hydrostatic pressure variation, namely P plus rho gz, as this one. So this is what we discussed previously when we have the rho gz and rho g, the P, the pressure, and the gamma z. So and then we could simplify the pressure gradient in x direction is dp dx. So and this is the same for all value of y across the duct of any value of x. So this is the Navier Stokes equation in the x direction. So we have all of this. So and then for steady flow, fully developed flow, the left hand side of this equation reduced to zero. There is no acceleration in the x direction because the velocity is constant actually on the x direction, and the equation can be written as this one. So I hope you could see the previous notes about this, because I think this is the not the first time we talking about the Navier Stokes to simplify the Navier Stokes previous. So previously we show you how to get the velocity profile with the 2 times integration, and before that we simplify the Navier Stokes equation. So the same idea here actually. So and then because u is a function of y only, so we don't have the du and dx here, and dp dx is a function of x only, this equation can be simplified as this one. So the slope of the duct can be expressed as this one. So I think in the first slide we have this one. We assume that sine theta is equal to negative dz dx. So we substitute in the equation. So and then finally we could simplify the equation as this one. Okay, so this equation is actually the same equation as used in the previous section to obtain the velocity distribution. So and then from here, so we again we start the integral 2 times, and then we could solve the problem. So this is just to show how the representative solution for that the flow between 2 parallel plates derived directly from the Navier Stokes equation.